So I'm talking about the challenge protocol today, but you might not know what the challenge protocol is. It's kind of internal to Arbitrum in that as a user who's deploying smart contracts on Arbitrum or doing transactions on Arbitrum, you don't really have to care about the challenge protocol or how it works, and that's intentional. We want to hide this from users and keep it as something where you can assume that Arbitrum is secure without having to worry about how it's secure unless you're actually diving into that protocol. But this isn't something you need to worry about when you're writing your own smart contracts for Arbitrum. So let's get into it. The challenge protocol is the fraud-proof implementation. It's how validators dispute assertions about L2 state and prove that state to layer 1 in order to complete withdrawals. So what does that mean? When you're withdrawing your funds from Arbitrum to Ethereum, Ethereum needs to somehow know who has balance, how much balance they have, and that sort of thing. You can't just allow anyone to withdraw an arbitrary sum of money. That you need to know that they have balance on Arbitrum. And to do that, optimistic rollups use fraud proofs to allow any validator to assert a certain state has happened. A validator might assert that someone has one Ethereum on Arbitrum, and then any other validator can challenge it, and that challenge will reveal who is correct and who is incorrect, who's honest and who's malicious. And the important part about this process is that only a single honest validator is necessary to prove the correct state. So this is a lot different from other protocols where you make assumptions about 2/3 of validators being honest, or an honest majority, or an honest quorum. You only need a single honest validator to dispute an incorrect assertion in order to defeat it. And that's because this isn't just a vote. It's not just validators say, oh, there's 5 saying this is correct and 2 saying it's not correct, so it must be correct. There's actually a protocol here that shows to Ethereum the correctness of an assertion, even if only one validator is advocating for it. I also wanted to talk about what the challenge protocol is not. So one key thing is that fraud proofs are all about outputs. They're all about the current state. They're not about inputs or transactions or what's happening. A fraud proof doesn't prevent an invalid transaction, for example. I could make a transaction on Arbitrum via the delayed inbox that says, I want to send 5 ETH to Bob, even if I don't have 5 ETH. I could post that transaction to the delayed inbox. But the Arbitrum chain would not give Bob 5 ETH because it would see that I don't have 5 ETH. Fraud proofs make sure that Bob doesn't get the 5 ETH. They don't make sure that I don't post a transaction. Posting to the inbox, as it's called, posting that transaction to the delayed inbox is permissionless and doesn't involve the challenge protocol. By the time the challenge protocol kicks into effect, the inputs, the transactions are already known and ordered. So for that reason, the challenge protocol doesn't govern batch posting, and the sequencer isn't involved at all. Those are all about determining the order of transactions and posting them to layer 1 Ethereum. They're not about, they're separate from the challenge protocol, which is all about determining the current state, determining balances, and that sort of thing. And the one last thing I wanted to cover is that only validators care about challenges, and normal L2 Arbitrum nodes do not care. And that's important because if a challenge happens, that doesn't mean there's a reorg on the Arbitrum chain. Arbitrum nodes already know the correct state. They know that if I make that transaction saying I'm sending 5 ETH when I don't have 5 ETH, they already know before a challenge happens that Bob doesn't get 5 ETH because they can just do the math locally. They can know what balance I have. They know that I don't have that ETH to send to Bob, so they won't give Bob the ETH. And normal Arbitrum nodes don't need a challenge for that reason. It's all about proving that state, that normal Arbitrum nodes, to layer 1, and that's where validators come in. So why that's super important is because a decentralized validator set is a lot more important than a decentralized sequencer. And that's because if all of the validators were malicious, they could just make an assertion that says, hey, we're going to take all of the bridge funds for ourselves. And if all of the validators were malicious and no one stepped in to challenge them, then they would get all of the bridge funds. That's not true of the sequencer. The sequencer can't just say, hey, I deserve all of the funds. The sequencer can order transactions. It could front run you. It could, but if the sequencer says, hey, I'm sending myself all the funds, everyone else is just going to ignore that, because the sequencer is about inputs, not about state, not about outputs, not about balances. That's where validators come into play. And that's why decentralizing the validator set is so important. And Arbitrum has already made great progress there. Arbitrum 1 already has a lot of different validators from a lot of different entities, including the Ethereum Foundation, for instance, runs an Arbitrum 1 validator. So let's look at an example challenge protocol. This one's going to be really simple, and we're going to find out later on that it's too simple, but it might show you what a challenge protocol is like. So let's look at a rollup in which there's only balance transfer. There's no Ethereum virtual machine, nothing complicated. Again, we're just looking at the simplest thing possible. So validators might post everybody's balance for every block to layer 1. Again, this is not how Arbitrum actually works, and this is not a good protocol, frankly, but it's very good for explaining what a challenge protocol is. So a validator might say that as of block 1, the Genesis block, let's say the validators agree that A has 1 ETH. And then let's say at block 2, A sends 0.5 ETH to B. Remember that that's a transaction that's not governed by the challenge protocol. That's part of the inbox. So by the time the challenge protocol takes effect, everyone, including layer 1 Ethereum, already has this transaction here. That's in the inbox, and it can't be challenged. But what can be challenged is this state here. This is the output state. Now, the output state is that A has 0.5 ETH and B has 0.5 ETH because A sent 0.5 to B. And both validators agree here. And if both validators agree and no one challenges that state for 7 days, then that's treated as correct. This Ethereum layer 1 never needs to actually execute the transactions in this block because all of the validators agree, and so there's consensus in a way. And even if one disagreed, though, we would need to enter the challenge protocol. So let's say that in the next block, B sends 0.5 ETH to themselves. And validator A correctly says, well, that doesn't change the balances at all, right? B remains at 0.5 ETH because they just sent it to themselves. But what if validator B said, actually, I think I have 1 ETH as a result of that? Well, that's not correct. They've just given themselves ETH. But how do we prove that to layer 1? Well, in this simplest challenge protocol, what we can do is we can re-execute. We can take this state that everyone agrees on, and we can re-execute the transaction in block B, which is that B sends 0.5 ETH to themselves. And then on layer 1, since there's a disagreement, we can see the layer 1 node can take that before state. They can subtract 0.5 ETH from B and then give that 0.5 ETH to B, executing the transaction and see, wait a minute, A is correct here. So A would win this challenge. And in a challenge protocol, you might have bonding where B is, where any validator is disincentivized from posting an incorrect assertion because they would put up a stake, a bond, that anyone who challenges their assertion and wins would get. And in a similar method, the challenger would also put up a bond that disincentivizes them from challenging a correct assertion because they lose that bond if they lose the challenge. But just sticking to the simplest challenge protocol here, to recap again, each validator would post a full state for each block. And then if there's disagreement, you can re-execute the block using the transactions stored in the inbox to figure out who's correct and who's incorrect. And this protocol already does some things, right? It means that usually you don't have to execute the transaction on Ethereum, and you get to save on that execution. Now, execution of a transaction is actually, in this protocol, not the expensive part. There's a bunch of other expensive things here. And this challenge protocol is much too simple for that reason. One really expensive part is that the full state is really expensive to post to layer 1. You don't want to have to be posting a full list of balances for every block to layer 1. What we can do instead is we can just post a hash of those balances. We can post a Merkle tree root, which commits to all of those balances, and using cryptography, it's a short 32-byte hash that commits to the full list of balances. And what that means is a validator can post something which is unique to a list of balances without posting the full list. And that, but even posting every block hash, and a block hash is basically the same thing. A block hash includes Merkle roots of all of the balances, of all of the state. What exactly this state is going to be depends on the rollup. Arbitrum is an EVM rollup. It doesn't just do balance transfers, so state's a lot more complicated. And instead of a Merkle root, we have a full block hash, which contains a bit of other info, like receipts, logs, that kind of thing. All of the normal Ethereum block contents. But even posting a block hash for every block is really expensive because, for instance, Arbitrum creates 4 blocks a second. That's a lot of storage if you were going to store all of those on Ethereum. So what you can do instead is you can only post a block hash, say, every hour. So if we go back to the previous slide, you can see here, instead of doing like block 1, block 2, block 3, maybe you would do block 100, block 200, block 300, and then instead of just one transaction or one block's transaction here, it would be 100 blocks worth of transaction. You can post batches of blocks and then post a block hash every hour or so. But then we start to run into an issue that you'd already have with an EVM rollup, which is that re-executing that full list of blocks might not fit in a layer 1 block. Well, what does that mean? So layer 1 blocks and therefore layer 1 transactions can only store up to 30 million gas. You can't just do unlimited computation in a layer 1 block, even if you have the ETH to pay for it. And that's intentional to prevent someone from just using up the Ethereum chain for forever. You need to be making blocks every 12 seconds. So you can't fit an infinite amount of computation in there. Ethereum limits it to 30 million gas. And Arbitrum's block gas limit is actually 32 million gas. So you might be seeing a problem there already. Even if it was smaller, we'd have problems. But you just can't fit all of that re-execution into a single layer 1 block, especially if you're posting a bunch of blocks at once. So to fix that, we can use an interactive challenge protocol. The challenge protocol we looked at before was non-interactive, which meant that as soon as a challenge occurred, we could replay that execution and instantly determine who was right and who was wrong. By re-executing this transaction, by re-executing this transaction here, the rollup protocol on layer 1 would instantly know who was correct and who was incorrect, because it could re-execute this transaction here against this state and see that validator A was correct and B was incorrect. With an interactive challenge protocol, things get more complicated because we use a binary search to narrow down the disagreement starting from, let's say a validator posted a batch of 4 blocks at once. And let's say that at the start of these 4 blocks, the validators agree on what the correct state is. But after these 4 blocks, the validators disagree about the correct state. Well, we could just re-execute these 4 blocks, except that might not fit. So an interactive challenge protocol breaks down the problem into parts. We first look at the middle, and we ask, and this is still a simplified version, by the way. In reality, instead of just breaking it down by 2, we ask validators about 30 points across this line. But let's look at a simplified version here, where we just ask both validators, hey, what do you have 2 blocks in? And let's say they both agree on the state. Let's say they both agree on the block hash, and they agree, therefore, on how much balance each account has and all of that. Well, now we've already actually halved the problem in half, because now we've turned a challenge about 4 blocks into a challenge about only 2 blocks, because they both agree about this part. So it's just a question of what happened over here. So then we break it down in half again. We do the same thing. We say 3 blocks in, what block hash does each validator have. And let's say they disagree there. Well, now we have a single block disagreement that we can re-execute here. And even if we couldn't re-execute the full 4 blocks, we can re-execute this 1 block. And we know that both validators agree at the start of it and disagree at the end of it. So therefore, we know that we can figure out which validator is honest and which one is malicious based on this 1 block alone. Now, as a side tangent here, to re-execute the block, we've talked about re-executing the block in Solidity, but the Arbitrum actually re-executes the block in WebAssembly. The state transition function, that is what processes the transactions and produces the output state. For our simple challenge protocol, the state transition function was just take the, subtract the transactions value out of the sender's account and give it to the output account. For Arbitrum, the state transition function is a lot more complicated. It involves invoking the Ethereum virtual machine, running smart contracts, RBOS, logs, all of this complicated stuff. And we have an implementation of this in Go that we can compile both natively to code that runs on the node software without any performance penalty, and we can compile it to WebAssembly. Rachel's talked about WebAssembly in a previous talk on Stylus, and it's great for a lot of the same reasons there, particularly here because it's an industry standard. We can write that Go code and compile it using the Go compiler without any modifications to WebAssembly, which we can do fraud proofs over. And another reason for this is we're going to get into next interactive challenges on the sub-block level, because I mentioned before that Arbitrum's block gas limit is still bigger than Ethereum's, and even if it wasn't, there's some overhead associated in challenges here. It would be really hard to fit it all in a single L1 Ethereum block. So we need a custom VM implementation anyways, and WebAssembly is a great choice here because it's an industry standard and we can reuse code that we already had written. Because otherwise, if we decided to stick with the EVM, we'd have to write an EVM implementation in the EVM, which is possible, but it's a lot easier to just reuse the Go implementation we have and compile it to WebAssembly. So let's look at how we break down the blocks, because a block might still be too big to completely re-execute on layer 1. We do the same bisection protocol here. So in practice, a single Arbitrum block takes billions of WebAssembly instructions to execute. And you can see why that's so complicated. There's no way that computation is going to fit in a single Ethereum block, not even close. But the good news about the bisection protocol is that it's logarithmic timed. And what that means is even billions of instructions can be challenged with only 30 bisection steps, which is very feasible. And those are split across multiple Ethereum blocks even. So in this example, though, we're just going to look at a block with only 4 opcodes in it. And we do the same thing. We ask them, hey, 2 opcodes in, do the validators agree or disagree? Now, instead of block hashes, we'll be looking at machine hashes here. In other words, the current state of that WebAssembly machine, because that WebAssembly machine takes in the inputs, which are any transactions in the previous block hash, and produces at the end an output block hash. And we know that the validators disagreed about what the block hash at the end of this block was, so they must therefore disagree about what the machine hash is at the end of this WebAssembly execution. So we can break this down and we say, hey, do you agree where the WebAssembly machine is in the middle? And let's say they disagree here. So again, we've broken the problem down in half. We do the same thing. We say halfway in, do you agree or disagree? Let's say they disagree again. And then we can re-execute this one WebAssembly opcode. What that might look like is, say the WebAssembly machine has a 2 and a 3 on the stack, and the next opcode is an add. What we can do is, in layer 1, we can re-execute that add, and then figure out what the new machine state is. In this case, the new machine state would just be a 5 on the stack, because 2 plus 3 is 5. And whichever validator said there was a 5 at this point will win. And that's really powerful, because this whole block execution is a super complex process, but with WebAssembly, we can break it down into very small steps. Something as complex as executing the entire Ethereum virtual machine, doing smart contracts, cryptography, hashing, logs, all of this very complicated stuff can be broken down into very simple WebAssembly instructions, like, what's the sum of 2 plus 3? It's really amazing when you think about it, that something so complex can be broken down into something so simple, but that's the power of abstraction. And we utilize that here in order to minimize the amount of work Layer 1 Ethereum needs to do to resolve a dispute. It only needs to execute one WebAssembly opcode per dispute. So, another thing about this simplified challenge protocol we've looked at, and this is also true of the current Arbitrum challenge protocol today, is that all honest validators must challenge a malicious validator. And why is that? Well, this challenge protocol is interactive, and what that means is you can make an incorrect move and intentionally lose your challenge. So let's say, for instance, looking at this example, let's say that this validator, instead of saying that they agreed with the so there's one validator here that's honest and one that's malicious. Let's say that the honest validator said that they disagreed with the dishonest validator halfway through. Now, instead of becoming a challenge about these second 2 blocks, the challenge becomes about these first 2 blocks. And what that means is the malicious validator could win this challenge because it would have the correct block hash midway through, and the honest validator would have said it disagrees with that. It would have made an incorrect statement midway through the challenge. Now, a truly honest validator would, of course, never make an assertion that it disagrees with the correct block hash midway through the challenge. But what if a malicious validator was pretending to be honest? This interactive challenge protocol has a bit of an issue, which is that you can't tell if another validator is honest or malicious until they complete the challenge process. And that means that every honest validator, if you want to have that one-of-n trust assumption, that trust assumption that only one honest validator is necessary to force the chain in the right direction, every honest validator needs to make their own challenge because they can't trust that other validators will make the same correct moves unless they also inherently trust that those other validators are honest, which is something we don't want. We want each validator to independently guarantee the security of the chain. So how can we fix this? How can we fix this? We can actually break the challenge protocol down into a graph. And how this works is very complicated. We're going to be releasing a paper on this at some point. But the essence of it is you can watch other validators do their challenges. And if you don't agree with a move they made, or if they simply don't make a move, you can pick up where they left off. So if you're midway through, if you're watching this challenge and you're midway through here and they either don't make this final move or they just stop making moves, you can pick up where they left off and say, hey, I'd like to make this move myself, and continue the challenge from there as your own separate challenge. And that allows honest validators, if someone's already running an honest validator that goes first, as Offchain Labs currently is, running a make nodes validator as it's called, which makes new assertions about the state and is the first to act, other honest validators in the current challenge protocol would also need to defend those assertions if they see an incorrect one. They also need to be challenging. But with the new challenge protocol, other honest validators can sit on the sidelines unless the primary validator makes a mistake or doesn't respond, in which case the other validators will jump in and make the move. But under normal circumstances, they can just sit on the sidelines, which is great because it means that running an honest validator is normally free. Because of the fact that normally another honest validator will be making the moves for you, you can defend the chain for free under normal circumstances and have that confidence that the Arbitrum chain will reach the correct results. And this is also very important for permissionless validation, both because you don't want to be wasting a ton of money whenever a malicious assertion happens on all of the honest validators challenging, but also the new challenge protocol provides strong bounds on delay attacks, which are where you issue a challenge which takes time to delay withdrawals. You don't want the chain to just be constantly delayed and withdrawals aren't going through because someone is just issuing these challenges that they will eventually lose, but the key word there is eventually. And the new challenge protocol provides strong bounds on delay attacks, which is very important for permissionless validation, where anyone can come in and be that one honest validator, even on your own computer. Thank you, everyone. Have a nice day.